Thank you for selecting this video. If you find it enjoyable, please like and subscribe to help this channel grow. It would help immensely. Now let's begin the journey. Close your eyes and imagine darkness. Not the darkness of a moonless night, but something far deeper. The darkness that existed before anything at all. 13.8 billion years ago, there was no space, no time, not even emptiness as we understand it. And then, in an instant smaller than you can possibly imagine, everything began. The Big Bang wasn't an explosion in space, it was an explosion of space itself. In less than a trillionth of a second, the entire universe expanded from something smaller than an atom to something larger than a galaxy. It's almost impossible to comprehend, but in that first fraction of a moment, all the energy that would ever exist in our universe came into being, spreading outward in every direction at once. For the first few minutes after this beginning, the universe was unimaginably hot, about 10 billion degrees. Nothing solid could exist. There were no stars, no planets, not even atoms as we know them. Just a sea of pure energy and the smallest building blocks of matter colliding and dancing in the cosmic fire. And yet, within just 3 minutes of existence, something remarkable happened. As the universe cooled ever so slightly, the very first atomic nuclei began to form, mostly hydrogen with a sprinkling of helium. These would become the seeds of everything. For the next 380,000 years, the universe remained opaque, filled with a fog of particles and light that couldn't travel freely. Imagine a cosmic cloud so thick that light itself couldn't escape. But then, as the temperature dropped below about 3,000 degrees, something beautiful occurred. Electrons and nuclei combined to form the first complete atoms, and suddenly light could travel. The universe became transparent, and that ancient light is still traveling through space today. We call it the cosmic microwave background radiation, a faint whisper of warmth that fills every corner of the universe, a baby picture of creation itself that we can still detect with our instruments. But the universe was still dark in a different way. There were no stars yet. For perhaps 200 million years, the cosmos existed in what scientists poetically call the Dark Ages. Clouds of hydrogen gas drifted through space, growing denser in some places, thinner in others, pulled together by the invisible hand of gravity. These clouds were patient, gathering slowly, waiting for the moment when they would finally ignite. When the first stars finally lit up, they transformed everything. These weren't like our sun. They were monsters, perhaps 100 or even 1,000 times more massive, burning with fierce blue-white light. Their lives were brief but spectacular, lasting only a few million years before dying in tremendous explosions called supernovas. And in those violent deaths, something essential happened. The intense heat and pressure forged new elements: carbon, oxygen, iron, gold, all the heavy elements that make up planets, and eventually life itself. Every atom in your body heavier than hydrogen was created in the heart of a dying star billions of years ago. You are quite literally made of stardust. These early stars and their explosive deaths enriched the universe, seeding space with the raw materials for something more complex. Clouds of gas and dust began to collapse again, but this time they contained not just hydrogen and helium, but all these new elements. About 9.2 billion years ago, in one such cloud in an unremarkable region of space, our own sun began to form, gathering material around it that would eventually become the planets, moons, and everything in our solar system. The universe had set the stage for us slowly and patiently over billions of years. From that first moment of creation to the birth of our own star, the cosmos had been preparing, mixing its elements like ingredients in a cosmic recipe, stirring matter across distances we can barely fathom. And all of this happened in near silence, in the vast quiet of space where there is no air to carry sound, just light and matter dancing their ancient dance across the expanding darkness. Fade to next segment. Example. Great. Can you please continue this with 8 more facts spread across 10 minutes of script? December 26th, The Cosmic Lullaby, a journey through the universe. Script for minutes, 10 to 20. Our sun, that familiar golden light that warms your face on a summer day, is just one star among hundreds of billions. It sits in a galaxy we call the Milky Way, a vast spiral of stars, gas and dust spanning 100,000 light-years from edge to edge. To travel from one side to the other at the speed of light, moving at 186,000 miles per second, would take you 100,000 years. And yet, our galaxy is just one island in an ocean of galaxies, each containing their own hundreds of billions of stars. The Milky Way is ancient, formed roughly 13.6 billion years ago, just 200 million years after the Big Bang itself. It's a graceful spiral with sweeping arms of stars, and our sun resides about halfway out from the center in a quiet, suburban neighborhood of the galaxy called the Orion Arm. We orbit the galactic center at an incredible speed, about 515,000 miles per hour, and yet it takes us approximately 230 million years to complete just one orbit. The last time our solar system was in this exact position, dinosaurs had not yet appeared on Earth. At the heart of our galaxy lies something both terrifying and magnificent, a supermassive black hole called Sagittarius A star. This cosmic giant contains the mass of about 4 million suns, all compressed into a region smaller than our solar system. Black holes are perhaps the universe's most enigmatic objects, regions where gravity is so intense that not even light can escape. They bend space and time around themselves, creating a point of no return called the event horizon. Cross that boundary and you can never come back. Time itself behaves strangely near a black hole. If you could somehow survive near the event horizon, time would pass much more slowly for you than for someone far away. An hour for you might be 7 years for them. But don't worry, black holes, despite their fearsome reputation, are not cosmic vacuum cleaners. They don't roam around swallowing everything in sight. If our sun was suddenly replaced by a black hole of the same mass, Earth would continue orbiting exactly as it does now, just in permanent darkness. Black holes only consume matter that ventures too close, and the nearest known black hole to Earth is still safely about 1,600 light-years away, so distant that its light takes 16 centuries to reach us. Our galaxy isn't alone in its journey through space. The Milky Way has dozens of smaller satellite galaxies orbiting it, like moths around a flame. The two largest are the Large and Small Magellanic Clouds, visible from the southern hemisphere as hazy patches of light. These dwarf galaxies are slowly being pulled apart by our galaxy's gravity, their stars gradually becoming part of the Milky Way. In about 4.5 billion years, something even more dramatic will occur. Our galaxy will collide with our nearest large neighbor, the Andromeda Galaxy. Don't worry, this is not a violent crash as you might imagine. Galaxies are mostly empty space, and when they merge, it's more like two clouds passing through each other, a slow cosmic dance that will take millions of years to complete. As you lie here, breathing slowly, the light from distant stars is falling on your closed eyelids, light that has been traveling for years, decades, even centuries. When you look at the night sky, you're seeing the universe not as it is, but as it was. The light from the nearest star beyond our sun, Proxima Centauri, takes 4.2 years to reach us, so we see it as it appeared 4 years ago. Some stars visible to the naked eye are hundreds of light years away. We see them as they were when your great-great-great-grandparents walked the Earth. The universe is so vast that it takes time itself for for information to cross it, and in looking outward, we're always looking backward through time. This creates a strange and wonderful truth. The deeper we look into space with our telescopes, the further back in time we see. The most distant galaxies we've observed appear as they were more than 13 billion years ago, when the universe was young and those galaxies were just forming. We can actually see cosmic history unfolding before us, like reading a book written in light across billions of years. The universe is not just large in space, it's deep in time, and every direction we look offers a window into the past. Between all these stars and galaxies lies something unexpected, mostly emptiness. The universe is far more empty than full. If you could somehow remove all the stars, planets, and gas from a galaxy, the shape would still remain, held together by something invisible, something we can't directly see or touch. Scientists call it dark matter, and it makes up about 85% of all matter in the universe. We know it exists because we can see its gravitational effects. Galaxies spin too fast to hold together based on visible matter alone, and galaxy clusters bend light in ways that reveal far more mass than we can account for. Dark matter is the universe's greatest ghost, everywhere and nowhere, holding the cosmos together with invisible hands while remaining stubbornly mysterious. We still don't know what it's made of. The universe is teaching us humility. Everything we've ever seen, every star, every planet, every galaxy, every atom in your body, all the normal matter we know accounts for less than 5% of everything that exists. The rest is dark matter and something even stranger called dark energy, a mysterious force causing the universe's expansion to accelerate. We live in a cosmos where we understand only the smallest fraction of what's really there, floating like a leaf on an ocean whose depths we've barely begun to explore. Fade to next segment. Example. Great. Can you please continue this with 8 more facts, spread across 10 minutes of script, December 26th. The Cosmic Lullaby, a journey through the universe. Script for minutes, 20 to 30. Let's return now to something closer to home, to the star that makes all life possible. Our Sun is a middle-aged star, about 4.6 billion years old, roughly halfway through its life. Every second, deep in its core, the Sun converts about 600 million tons of hydrogen into helium through nuclear fusion. This process releases an enormous amount of energy, the equivalent of billions of nuclear bombs exploding every single second. And yet that energy takes a surprisingly long time to reach us. A photon of light created in the Sun's core doesn't simply zip straight out into space. Instead, it bounces around inside the Sun, colliding with atoms, being absorbed and re-emitted countless times in a random walk that can take between 10,000 and 170,000 years before it finally reaches the surface. Only then does it speed across the 93 million miles to Earth in just 8 minutes. The sunlight touching your skin right now began its journey in the heart of the Sun before humans even existed. The Sun is incomprehensibly large. You could fit about 1.3 million Earths inside it. And yet in the grand scheme of the universe, it's actually quite average, even small. There are stars so massive that if you placed one where our Sun sits, its surface would extend beyond the orbit of Jupiter. The largest known star, Stephenson 2-18, is nearly 2,000 times wider than our Sun. If you could somehow fly around it at the speed of a commercial airplane, the journey would take about 900 years. But size isn't everything in the stellar world. The brightest stars aren't always the biggest, and the biggest aren't always the brightest. Stars come in a rainbow of colors that tell us their temperature. The coolest stars glow red, with surface temperatures around 3,000 degrees Celsius. Stars like our Sun burn yellow-white at about 5,500 degrees. The hottest stars blaze blue-white at temperatures exceeding 30,000 degrees. These blue giants are the universe's extravagant spenders, burning through their fuel at a reckless pace. While our sun will shine steadily for about 10 billion years, a massive blue star might last only a few million, a cosmic blink of an eye. When stars die, they die in different ways depending on their mass. Stars similar to our sun will end their lives more gently. In about 5 billion years, our sun will exhaust its hydrogen fuel and begin burning helium. It will swell into a red giant, growing so large that it will likely engulf Mercury, Venus, and possibly even Earth. For a brief time, just a few 100 million years, it will shine with a luminous red glow, perhaps 100 times brighter than it is today. Then, unable to sustain fusion any longer, it will shed its outer layers in beautiful clouds of gas called a planetary nebula, leaving behind a small, dense core called a white dwarf. This remnant will be about the size of Earth, but incredibly dense. A teaspoon of white dwarf material would weigh about 15 tons on Earth. It will slowly cool over trillions of years, eventually becoming a black dwarf, a cold, dark cinder drifting through space. More massive stars meet more violent ends. When a star at least 8 times more massive than our Sun exhausts its fuel, something catastrophic happens. The core collapses in less than a second, and the outer layers rebound in a spectacular supernova explosion that can briefly outshine an entire galaxy. These explosions are so powerful they can be seen from millions of light years away. In 1987, a supernova occurred in the Large Magellanic Cloud, visible to the naked eye from Earth, the closest supernova observed in nearly 400 years. The star that exploded had been there in our night sky, and then suddenly it wasn't. In its place was a brilliant new light, a star's death announcement written across the cosmos. What remains after a supernova depends on the original star's mass. For some, the core collapses into a neutron star, an object so dense that a sugar cube-sized amount would weigh as much as all of humanity combined. Neutron stars are typically only about 12 miles across, smaller than most cities, yet they contain more mass than our entire sun. Some neutron stars spin rapidly, hundreds of times per second, sending out beams of radiation like cosmic lighthouses. We call these pulsars, and they keep time more accurately than any clock we've ever built. The millisecond pulsars are nature's most precise timekeepers, rotating with such regularity that they rival atomic clocks. For the most massive stars, even a neutron star cannot support the core's collapse. Gravity wins completely, crushing everything into a black hole. Nothing in the known universe can stop this collapse. The matter doesn't become anything else. It simply compresses toward an infinitely small point called a singularity, where the laws of physics as we understand them break down completely. Near a black hole, time and space become so warped that they almost exchange roles. The usual rules stop applying. It's a place where the universe itself seems to reach its limit, where our mathematics encounters infinities and our understanding reaches its boundary. Between the stars, in the vast spaces you might think are empty, float clouds of gas and dust called nebulae. Some are the birthplaces of stars, vast stellar nurseries where gravity slowly pulls matter together. The Orion Nebula, visible to the naked eye as a fuzzy patch in the constellation Orion, is one such nursery, only about 1,300 light-years away. Inside it, new stars are forming right now, their light beginning to push away the surrounding gas, creating intricate sculptures of glowing matter. Other nebulae are the remnants of dead stars, like the Crab Nebula, the scattered remains of a star that exploded nearly 1,000 years ago, still expanding outward at millions of miles per hour. These nebulae glow in stunning colors, reds from hydrogen, blues and greens from oxygen, creating cosmic artwork on the largest canvas imaginable. The universe is an endless cycle of birth and death, creation and destruction. Stars are born from the ashes of earlier stars, live their brilliant lives and die, scattering their enriched material back into space to become the next generation. Every star is connected to every other star through this cosmic inheritance, all of them part of one great family tree, stretching back to the very first lights that broke the cosmic darkness. And we are part of that story too, made from the same stardust, children of stars that died long before our world even existed. Fade to next segment. Example. Great. Can you please continue this with 8 more facts, spread across 10 minutes of script? December 26th, The Cosmic Lullaby, A Journey Through the Universe. Script for minutes 30 to 40. Now let's journey closer to home, to the place we call our own, our solar system, a small family of worlds bound together by the sun's gravity. 8 planets circle our star, each one a unique world with its own story to tell. They fall into 2 groups, the 4 inner rocky planets, small and solid, and the 4 outer gas and ice giants, massive worlds of swirling storms and frozen mysteries. Mercury, the closest planet to the Sun, is a world of extremes. During its day, which lasts 59 Earth days, temperatures can soar to 430 degrees Celsius, hot enough to melt lead. But Mercury has almost no atmosphere to trap heat, so at night, temperatures plummet to minus 180 degrees Celsius. This makes Mercury the planet with the greatest temperature variation in our entire solar system, swinging more than 600 degrees between day and night. Standing on Mercury's surface, you would see the Sun appear almost 3 times larger than it does from Earth, blazing in a black sky because Mercury, like our Moon, has no atmosphere to scatter light and create a blue sky. Venus, often called Earth's twin because of its similar size, is actually a vision of hell. Hidden beneath brilliant white clouds that reflect sunlight beautifully, making Venus the brightest planet in our night sky, lies a surface where the temperature reaches 465 degrees Celsius, hot enough to melt zinc, and actually hotter than Mercury, despite being nearly twice as far from the Sun. The reason is Venus's thick atmosphere, made mostly of carbon dioxide, which creates a runaway greenhouse effect. The atmospheric pressure on Venus's surface is 92 times greater than Earth's, equivalent to being a kilometer underwater in Earth's oceans. If you could somehow stand on Venus, you would be simultaneously crushed, incinerated, and dissolved by clouds of sulfuric acid drifting through the sky. It's a cautionary tale written in planetary form, showing what can happen when greenhouse gases spiral out of control. Then there's Earth, our home, the only place in the universe where we know life exists. What makes Earth special isn't just its perfect distance from the Sun, though that helps. It's a combination of factors: liquid water covering 71% of its surface, a protective magnetic field generated by its molten iron core that shields us from harmful solar radiation, and an atmosphere thick enough to keep us warm but transparent enough to let sunlight through. Earth is the only planet in our solar system with plate tectonics, its surface broken into massive plates that slowly drift, collide, and slide beneath one another. This constant recycling of the surface helps regulate the climate over geological timescales and may be essential for complex life. We are living on an active, breathing world, one that has been continuously inhabited by life for at least 3.7 billion years, perhaps longer. Beyond Earth lies Mars, the red planet, colored by iron oxide, rust, covering its surface. Mars is about half the size of Earth, with a day that lasts 24 hours and 37 minutes, remarkably similar to our own. But Mars is a cold desert world now, with an average temperature of minus 63 degrees Celsius. Its atmosphere is less than 1% as thick as Earth's, too thin to support liquid water on the surface today. And yet Mars tells a different story in its past. We've found ancient river valleys, vast plains that may once have been ocean beds, and minerals that form only in the presence of water. Billions of years ago, Mars may have been a warmer, wetter world, perhaps even suitable for life. What happened to that ancient Mars? Its small size meant its interior cooled faster than Earth's. Its magnetic field died, and without that protection, solar wind slowly stripped away its atmosphere over millions of years, leaving the frozen desert we see today. Between Mars and Jupiter lies the asteroid belt, a region containing millions of rocky bodies ranging from tiny pebbles to Ceres, a dwarf planet nearly 600 miles across. These asteroids are the leftover building blocks of planet formation, material that never quite coalesced into a world because Jupiter's immense gravity kept stirring things up, preventing the rocks from gathering together. The asteroid belt sounds crowded, but in reality, these objects are spread across such vast distances that if you were standing on one asteroid, you likely wouldn't be able to see any others with the naked eye. Space is mostly empty, even in the places where things gather. Then we reach the true giant of our solar system, Jupiter, a planet so massive that you could fit all the other planets inside it and still have room to spare. Jupiter contains 2.5 times the mass of all the other planets combined. It's not a rocky world like Earth. Jupiter is made mostly of hydrogen and helium, more like a star that never quite made it. If Jupiter had been about 80 times more massive, it would have ignited fusion in its core and become a second sun, making our solar system a binary star system. Instead, Jupiter radiates more heat than it receives from the Sun, still slowly contracting and releasing the energy from its formation billions of years ago. Jupiter's most famous feature is the Great Red Spot, a storm so large that 2 or 3 Earths could fit inside it. This hurricane has been raging for at least 190 years, possibly much longer since we first observed it, and it shows no signs of stopping, though it has been slowly shrinking over the past century. The winds in this storm reach speeds of 270 miles per hour. Jupiter's rapid rotation, it spins once every 10 hours despite its enormous size, creates powerful bands of wind that circle the planet, giving it distinctive stripes of color. These are not just clouds, but entire weather systems larger than our world, driven by heat welling up from deep within the planet. Jupiter serves as a cosmic protector for Earth. Its immense gravity acts like a vacuum cleaner, attracting comets and asteroids that might otherwise travel toward the inner solar system. In 1994, astronomers watched as comet Shoemaker-Levy 9 broke apart and slammed into Jupiter in a spectacular series of impacts, each explosion creating fireballs larger than Earth. Without Jupiter's gravitational influence, Earth would be struck by dangerous asteroids far more frequently, perhaps too frequently for complex life to have evolved. We owe our existence, in part, to this giant guardian planet, silently sweeping up cosmic debris for billions of years. The universe is not just vast in space, it's intricate in its connections. Every piece affects every other piece, from the gravity of Jupiter protecting Earth, to the death of ancient stars creating the atoms in your body, to the invisible dark matter holding galaxies together. You are part of this web, connected to everything, a small but essential thread in the cosmic tapestry. Fade to next segment. Example. Great. Can you please continue this with 8 more facts spread across 10 minutes of script? December 26th, The Cosmic Lullaby, A Journey Through the Universe. Script for minutes, 40 to 50. Beyond Jupiter, we venture into the outer reaches of our solar system, where sunlight grows dim and temperatures plunge to the cold of deep space. Here we find Saturn, perhaps the most beautiful planet in our cosmic neighborhood, adorned with its magnificent rings. Saturn is the second largest planet, another gas giant made mostly of hydrogen and helium, but it has a remarkable property. It's the least dense planet in our solar system. In fact, Saturn is less dense than water. If you could find an ocean large enough, Saturn would float. This bloated giant is so light for its size because it's mostly gas, with only a small rocky core buried deep beneath thousands of miles of atmosphere. But it's Saturn's rings that truly captivate us. Stretching over 280,000 kilometers from edge to edge, nearly 3/4 of the distance from Earth to the Moon, these rings are actually made of countless pieces of ice and rock, ranging in size from tiny grains to house-sized boulders. Despite their vast span, the rings are remarkably thin, in most places only about 10 meters thick. Imagine a disk the size of a football field, but thinner than a sheet of paper, and you'll begin to understand their delicate nature. The rings aren't solid, they're more like a traffic jam of billions of orbiting particles, each one a tiny moon following its own path around Saturn. We still don't know exactly how old Saturn's rings are. They might have formed with the planet 4.5 billion years ago, or they might be much younger, perhaps only a few 100 million years old, the remnants of a moon that ventured too close and was torn apart by Saturn's gravity. Uranus, the 7th planet from the Sun, is tilted on its side in the most unusual way. While most planets spin roughly upright like tops, Uranus rotates at a 98-degree angle, essentially rolling around the Sun like a ball. And this means that for part of its 84-year orbit, one pole faces the Sun continuously for 42 years of daylight, while the other endures 42 years of darkness. Then they switch. We don't know what caused this extreme tilt, but most astronomers believe Uranus suffered a massive collision early in its history, perhaps with another planet-sized object, that knocked it onto its side. Uranus is an ice giant, its interior composed of water, methane, and ammonia ices surrounding a rocky core, all wrapped in an atmosphere of hydrogen and helium. That methane in its atmosphere gives Uranus its distinctive blue-green color, absorbing red light and reflecting blue. Neptune, the 8th and final planet, is a deep, rich, blue world even more distant from the Sun. At this range, nearly 3 billion miles away, the Sun appears 30 times dimmer than it does from Earth, barely more than a bright star in Neptune's sky. And yet, despite receiving so little energy from the Sun, Neptune has the fastest winds in the solar system, reaching speeds of 1,200 miles per hour, faster than the speed of sound on Earth. These supersonic winds howl around the planet in the opposite direction to its rotation, driven by heat rising from Neptune's interior. Like Uranus, Neptune is an ice giant, but it radiates 2.6 times more energy than it receives from the Sun, powered by some internal heat source we don't fully understand. Perhaps it's still contracting from its formation, perhaps something else entirely. Neptune keeps its secrets well. For many years we counted 9 planets, with Pluto being the smallest and most distant. But in 2006, astronomers made the difficult decision to reclassify Pluto as a dwarf planet. This wasn't about diminishing Pluto, it was about understanding our solar system better. Beyond Neptune lies the Kuiper Belt, a vast region filled with thousands of icy bodies, remnants from the solar system's formation. Pluto is just one of many large objects there, not even the largest. That honor goes to Eris, which is slightly more massive than Pluto. These worlds are fascinating in their own right. Pluto has a heart-shaped region on its surface made of nitrogen ice, 5 moons including Charon, which is so large that Pluto and Charon actually orbit each other like a double planet, and even a thin atmosphere that freezes and falls to the ground when Pluto moves farther from the Sun in its elliptical orbit. Even farther out, beyond the Kuiper Belt, lies the Oort cloud, a theoretical spherical shell of icy objects surrounding our entire solar system. This cloud begins about 2,000 times farther from the Sun than Earth is and extends perhaps halfway to the nearest star. It's so distant that objects there take millions of years to complete one orbit around the Sun. The Oort cloud is thought to contain billions or even trillions of comets, most no larger than mountains, frozen in the darkness at the very edge of the Sun's gravitational influence. Occasionally, a passing star or gravitational disturbance nudges one of these icy wanderers, sending it falling toward the inner solar system, where the Sun's heat vaporizes its ice, creating a glowing tail of gas and dust, a comet, a visitor from the edge of our cosmic neighborhood, offering us a glimpse of material unchanged since the solar system's birth. Our solar system is far larger than the planets suggest. If Earth were the size of a marble, the Sun would be a sphere 8 feet across, and you'd need to walk about 60 feet to reach Mars. But Neptune would be more than a mile away, and the Oort cloud would extend for 30,000 miles. The distances are almost incomprehensible, and yet this entire vast domain is just a tiny pinprick in our galaxy, which itself is just one among billions of galaxies. Scale upon scale upon scale, each one dwarfing the last. Throughout our solar system on many worlds, we've found surprises that challenge our understanding of where life might exist. Jupiter's moon. Europa has an ocean of liquid water beneath its icy crust, kept warm by tidal heating from Jupiter's gravity flexing the moon. Saturn's moon Enceladus shoots geysers of water into space from a subsurface ocean, and its moon Titan has lakes and rivers of liquid methane on its surface, the only world besides Earth with stable bodies of liquid on its surface. These moons remind us that habitable might mean something different than we thought. Life, if it's out there, might not need a planet like Earth. It might thrive in the dark oceans of ice moons, never seeing a star, living off chemical energy from volcanic vents, the way some life does in Earth's deepest oceans. The solar system is our home, but it's also our laboratory for understanding how planets form and evolve, our preview of the countless other planetary systems we've discovered around distant stars. Every world tells a story of formation, evolution, and the endless interplay between matter and energy that shapes everything in the universe. From Mercury's scorched surface to Neptune's supersonic winds, from Saturn's delicate rings to Europa's hidden ocean, each world is a chapter in a larger story, the story of how stars and planets and moons come to be, and perhaps how life finds a way. Fade to next segment example. Great. Can you please continue this with 8 more facts spread across 10 minutes of script, December 26th. The Cosmic Lullaby, a journey through the universe, script for minutes 50 to 60. Let's step back now and look beyond our solar system, out to the stars that share our galaxy. For most of human history, we wondered whether our sun was unique in having planets, or if other stars had worlds of their own. That question was finally answered in 1992, when astronomers detected the first planets orbiting a star other than our Sun. These weren't orbiting a normal star, though. They circled a pulsar, the rapidly spinning remnant of a dead star. It would be 3 more years, in 1995, before we discovered the first planet orbiting a Sun-like star. That planet, called 51 Pegasi b, was strange by our standards. A gas giant larger than Jupiter, but orbiting its star in just 4 days, so close that its surface temperature exceeds 1,000 degrees Celsius. We now call these hot Jupiters, and they've taught us that planetary systems can be wildly different from our own. Since then, we've discovered more than 5,000 confirmed exoplanets, planets orbiting other stars, with thousands more candidates waiting to be verified. These worlds come in astonishing variety. Some are rocky super-Earths, larger than our world but smaller than Neptune. Others are puffy gas giants with densities less than styrofoam. We've found planets orbiting binary star systems where two suns rise and set in alien skies. We've discovered rogue planets wandering through the galaxy untethered to any star, drifting alone through the cosmic darkness. Some planets orbit so close to their stars that their years last mere hours, while others take thousands of years to complete one orbit. The universe's imagination, it seems, far exceeds our own. Among all these discoveries, one question drives us forward. Are we alone? To search for life beyond Earth, we look for planets in what we call the habitable zone, the region around a star where temperatures allow liquid water to exist on a planet's surface. Water, as far as we know, is essential for life. It's an excellent solvent, remains liquid over a wide temperature range, and has unique properties that make it perfect for the chemistry of life. We've found dozens of planets in their stars' habitable zones, worlds that might perhaps have oceans and rain and clouds like Earth. But being in the habitable zone doesn't guarantee life. Venus is technically in our Sun's habitable zone, yet it's a scorching hellscape. Still, these worlds give us hope, places to point our telescopes and search for signs. The nearest potentially habitable exoplanet we've found orbits Proxima Centauri, the closest star to our Sun, at just 4.2 light-years away. This planet, called Proxima Centauri b, is roughly Earth-sized and orbits within its star's habitable zone. But Proxima Centauri is a red dwarf, much smaller and cooler than our Sun, and red dwarfs are temperamental stars prone to violent flares that could strip away a planet's atmosphere. We don't yet know if Proxima b could truly support life, but the fact that the nearest star to us has a planet in the habitable zone suggests these worlds might be common. If you could travel at the speed of light, you could reach Proxima Centauri b in just over 4 years. But with our current fastest spacecraft, the journey would take about 70,000 years, a humbling reminder of the distances involved. Looking for life on distant planets is extraordinarily difficult. We can't see the planets directly in most cases. They're far too small and dim compared to their brilliant stars. Instead, we detect them indirectly. The most successful method watches for tiny dips in a star's brightness when a planet passes in front of it, blocking a fraction of the star's light. By measuring how much light is blocked and how often, we can determine the planet's size and orbital period. Some planets reveal themselves through their gravitational pull on their star, causing the star to wobble slightly as planet and star orbit their common center of mass. These indirect methods work, but they tell us little about what these worlds are actually like. To truly understand an exoplanet, we need to study its atmosphere, and we're just beginning to learn how. When a planet passes in front of its star, some of the star's light filters through the planet's atmosphere before reaching us. Different gases absorb different wavelengths of light, leaving fingerprints we can detect. Using this technique, we've found water vapor in the atmospheres of several exoplanets, along with methane, sodium, and other compounds. We're now searching for biosignatures, combinations of gases that might indicate life. On Earth, oxygen makes up 21% of our atmosphere, but almost all of it is produced by living things through photosynthesis. Without life constantly replenishing it, Earth's oxygen would react with rocks and disappear in just a few million years. If we found oxygen, especially alongside methane, in an exoplanet's atmosphere, it would be a tantalizing hint that something might be alive there. The James Webb Space Telescope, launched in 2021, has opened a new window into exoplanet atmospheres. This telescope orbits the Sun about 1 million miles from Earth, far from our planet's infrared-blocking atmosphere, and it observes the universe in infrared light, perfect for studying the heat signatures of distant worlds. Webb has already detected carbon dioxide in an exoplanet's atmosphere, studied the weather patterns on hot Jupiters, and examined rocky planets around nearby stars. Each observation brings us closer to answering that fundamental question. Is Earth unique, or is life common in the universe? Every time we point our telescopes at a new world, we're essentially opening a letter from the cosmos, wondering what message it might contain. But even if we find signs of life on another planet, making contact would be another matter entirely. The fastest we've ever sent information through space is at the speed of light, radio waves which travel at this cosmic speed limit. If we sent a message to Proxima Centauri b, it would take 4.2 years to arrive, and if anyone there received it and responded immediately, we'd wait another 4.2 years for their reply. A simple conversation would take nearly a decade, question and answer separated by years of silence. For more distant worlds, hundreds or thousands of light years away, communication becomes impractical. We might detect each other, but we'd be like ships passing in the night, acknowledging each other's existence across an unbridgeable gulf of space and time. Perhaps the most profound realization from discovering all these exoplanets is how common planetary systems appear to be. Nearly every star we examine closely has planets. Our galaxy likely contains hundreds of billions of planets, more planets than stars. And if even a tiny fraction of those planets harbor life, the universe could be teeming with living worlds. We might be surrounded by life, by consciousness, by entire civilizations, all of us separated by distances so vast that we may never meet, never touch, never share our stories. We are islands of warmth in the cosmic ocean, each world a small candle in the darkness, perhaps never knowing how many other candles are burning in the night. Fade to next segment. Example. Great. Can you please continue this with 8 more facts, spread across 10 minutes of script, December 26th, The Cosmic Lullaby, A Journey Through the Universe, script for minutes 60 to 70. As we gaze deeper into the universe, we must consider the possibility that we are not alone, that somewhere among those hundreds of billions of planets, other minds might be looking back at us. This question has captivated humanity for generations. Where is everybody? In 1950, physicist Enrico Fermi asked this very question over lunch with colleagues, and it's now known as the Fermi paradox. If the universe is so vast, if planets are so common, if life has had billions of years to emerge and evolve, then where are all the aliens? Why haven't we seen any evidence of advanced civilizations? The silence is deafening, and it whispers uncomfortable possibilities. Perhaps life is far rarer than we hope. The conditions that led to life on Earth might require such a precise combination of factors that it happens only once in a galaxy or once in a universe. We needed the right star, the right distance, a large moon to stabilize our tilt, Jupiter to deflect asteroids, plate tectonics to recycle our atmosphere, a magnetic field to protect us. The list goes on. Maybe we won the cosmic lottery and the universe is mostly barren, with life flickering into existence only in the rarest of circumstances. Or perhaps life is common but complex life, animals, intelligence, civilization, requires additional improbable steps. Single-celled organisms appeared on Earth relatively quickly, but it took another 2 billion years for complex cells to evolve, and even longer for multicellular life. Maybe most living worlds never progress beyond microbes. There's another possibility, more sobering. Perhaps civilizations don't last very long. The universe is nearly 14 billion years old, but any given civilization might exist for only a brief moment in cosmic time, a few thousand years perhaps, before destroying itself through war, environmental collapse, or some technology we haven't yet imagined. If civilizations rise and fall like mayflies, separated by millions of years and thousands of light years, they might never overlap, never detect each other, forever alone in their brief moments of existence. We've only been broadcasting radio signals into space for about a century, a bubble of human noise expanding at the speed of light, now roughly 200 light years across. In a galaxy 100,000 light-years wide, our whisper has barely left the neighborhood. Since 1960, scientists have been listening for signals from intelligent civilizations through SETI, the search for extraterrestrial intelligence. Giant radio telescopes scan the skies, searching for patterns in the cosmic static that couldn't be natural, mathematical sequences or structured signals that would announce the presence of another technological society. We've listened to thousands of stars, scanning billions of frequency channels, and so far we've heard only silence. In 1977, a radio telescope in Ohio detected a signal so unusual that the astronomer monitoring it wrote "wow" in the margin, the famous "wow" signal. It lasted 72 seconds, came from the direction of the constellation Sagittarius, and has never been detected again despite multiple searches. Was it aliens? Probably not. Most likely, it was interference from a satellite or some natural phenomenon we don't understand. But for those 72 seconds, we allowed ourselves to hope. The challenge of finding alien intelligence is immense. We don't know what frequencies they might use or if they even use radio at all. Perhaps they communicate through laser pulses or gravitational waves or methods we haven't discovered yet. They might not want to be found, or they might have existed 1,000,000 years ago and already gone extinct. Or perhaps they're here in the galaxy with us, but they're so advanced that we're as invisible to them as ants are to us. We simply don't recognize each other as intelligent. We're trying to solve a puzzle while missing most of the pieces, searching for something we might not recognize even if we found it. But the universe has a speed limit, and that limit shapes everything. Nothing can travel faster than light, about 186,000 miles per second, or roughly 671 million miles per hour. This isn't just an engineering challenge we might overcome with better technology. It's a fundamental law of the universe, woven into the fabric of space and time itself. Albert Einstein showed us that space and time are connected, two aspects of a single thing called space-time, and as you move faster through space, you move slower through time. At the speed of light, time stops entirely. This means that even if we could somehow build a ship that travels at light speed, it would still take 4 years to reach the nearest star system, decades to reach interesting destinations, thousands of years to cross the galaxy. The universe is telling us something with this speed limit. You can explore, but you must be patient. Some have dreamed of workarounds, wormholes that tunnel through space-time, connecting distant points like a cosmic shortcut, or warp drives that compress space in front of a ship and expand it behind, allowing faster-than-light travel without technically violating the speed limit. These ideas emerge from the equations of general relativity, mathematically possible but requiring exotic matter with negative energy, something we've never found and might not exist. They remain beautiful mathematical dreams, reminders that physics allows us to imagine but doesn't promise to deliver. For now, the stars remain distant, separated by gulfs that would take generations to cross, even with our fastest ships. Yet despite these vast distances, we are connected to the wider universe in ways both profound and subtle. Cosmic rays, high-energy particles accelerated to nearly the speed of light by supernovas, black holes, and other violent events constantly rain down on Earth. About 100 cosmic rays pass through your body every second, most harmlessly, though occasionally one might strike DNA in a cell and cause a mutation. Over billions of years, cosmic rays have contributed to evolution, introducing random changes that natural selection could work with. We are shaped, in some small way, by the universe beyond our world, touched by particles that may have traveled for millions of years from distant galaxies before finally intersecting with Earth, and with you. The universe even has its own background music, a faint hum left over from the Big Bang. This cosmic microwave background radiation fills all of space, a nearly uniform glow at a temperature of just 2.7 degrees above absolute zero. When you tune an old analog television between channels, about 1% of the static you see is actually this ancient light, the afterglow of creation itself. We exist bathed in the remnants of the universe's birth, surrounded always by evidence of where we came from. Every direction we look, we see the past, light from distant stars and galaxies that has been traveling for so long that we observe these objects as they were millions or billions of years ago. We live in a universe where looking out means looking back, where distance and time are forever intertwined, where the farther we peer into space, the closer we come to witnessing the moment of creation itself. The universe is not just around us, it's in us, through us, part of us, in ways we're only beginning to understand. Fade to next segment. Example. Great. Can you please continue this with 8 more facts, spread across 10 minutes of script, December 26th, The Cosmic Lullaby, A Journey Through the Universe. Script for minutes 70 to 80. Let's journey now to the very fabric of reality itself, to the strange and beautiful laws that govern everything from the smallest particle to the largest galaxy. The universe operates according to rules, patterns woven so deeply into existence that we can describe them with mathematics. One of the most fundamental is gravity, the force that holds you to Earth, keeps the moon orbiting our planet, binds the solar system together, and shapes the structure of the entire cosmos. Gravity is, in many ways, the weakest of nature's fundamental forces. The electrical force holding atoms together is about 1,000,000 trillion times stronger. And yet gravity dominates at large scales because it only attracts, never repels, and it acts across infinite distances, growing weaker but never disappearing entirely. Isaac Newton first described gravity mathematically in the 1600s, showing that the same force that makes apples fall from trees also keeps planets in their orbits. But it was Albert Einstein who revealed what gravity truly is. In his general theory of relativity, published in 1915, Einstein showed that gravity isn't really a force at all. It's the curvature of space-time itself. Massive objects like stars and planets create dips in the fabric of space-time, like a heavy ball placed on a stretched rubber sheet. Other objects moving through space-time follow the curves, and we perceive this as gravitational attraction. Earth doesn't orbit the Sun because the Sun pulls on it. Earth orbits because it's following the straightest possible path through curved space-time. You're not being pulled down to Earth right now. You're trying to follow a straight line through curved space-time, and the ground is in your way, pushing up on you. Einstein's equations predicted something remarkable. When massive objects accelerate, like 2 black holes spiraling into each other, they should create ripples in space-time itself, spreading outward at the speed of light like waves on a pond. Einstein called these gravitational waves, but he doubted we'd ever detect them. The waves are incredibly faint by the time they reach Earth, stretching and squeezing space by less than the width of an atomic nucleus over several miles. For 100 years, gravitational waves remained theoretical, but in 2015, the LIGO experiment finally detected them. The signal came from 2 black holes, each about 30 times the mass of our Sun, that had spiraled together and merged 1.3 billion years ago. The collision released more energy in a fraction of a second than all the stars in the observable universe combined, and that energy rippled through space-time, traveling across the cosmos until, one September morning in 2015, it passed through Earth, moving our instruments by an impossibly tiny amount, but just enough to detect. This discovery opened a new way of observing the universe. Light has been our window to the cosmos for all of human history, but gravitational waves let us sense events that produce no light at all, like black hole mergers. We can now listen to the universe as well as look at it, hearing the cosmic symphony of colliding black holes and merging neutron stars. Each detection tells us about events so violent, so energetic, that they shake the very fabric of reality itself, sending news of their occurrence racing across billions of light years at the speed limit of the universe. But gravity isn't the only force shaping reality. At the smallest scales, quantum mechanics governs the behavior of atoms and subatomic particles, and its rules are profoundly strange. In the quantum world, particles don't have definite positions or velocities until you measure them. They exist in a state of probability, simultaneously here and there, moving at many speeds at once. An electron orbiting an atomic nucleus isn't a tiny ball following a path. It's more like a cloud of probability existing in many places at once until the moment you observe it, when the cloud instantly collapses into a single location. This isn't a limitation of our instruments or understanding. It appears to be the fundamental nature of reality at the quantum scale. Even stranger, particles that interact become entangled, their properties linked in ways that transcend distance. If you measure one particle's spin, you instantly know the spin of its entangled partner, even if that partner is on the other side of the galaxy. Einstein called this spooky action at a distance and believed it revealed a flaw in quantum mechanics. But experiments have proven that quantum entanglement is real. The universe permits this instantaneous connection, though it's carefully designed so you can't use entanglement to send information faster than light. Nature preserves its speed limit even in the quantum realm. The universe is stranger than we imagined, operating on rules that seem to violate common sense, yet these rules have never once failed an experimental test. Quantum mechanics and general relativity are both spectacularly successful theories, each proven correct countless times. But they're fundamentally incompatible. They describe reality using different mathematics, different assumptions, different rules. Quantum mechanics works beautifully for tiny things. General relativity works perfectly for large things. But in situations where both matter, like inside a black hole, or at the moment of the Big Bang, the equations break down, producing infinities and nonsense. For nearly a century, physicists have sought a theory of quantum gravity, a unified description that could reconcile these two pillars of modern physics. String theory, loop quantum gravity, and other candidates have been proposed, but none have been proven. We remain, for now, with two partial maps of reality, each excellent in its domain, but neither complete. The universe operates at scales almost impossible to comprehend. The smallest meaningful length in physics is the Planck length, about 1.6 times 10 to the negative 35th meters, so tiny that if an atom were magnified to the size of the observable universe, the Planck length would be about the size of a tree. At this scale, space-time itself becomes grainy, quantum foam, fluctuating, and uncertain. On the other end, the observable universe stretches about 93 billion light-years across. That's about 880 trillion meters. Between the smallest and largest scales, there's a factor of about 10 to the 60 power, a 1 followed by 60 zeros. The universe spans scales so vast that we can barely conceive of them, from quantum fluctuations tinier than we can imagine to cosmic structures larger than we can see. And throughout all these scales, through all the strangeness of quantum mechanics and the elegant curves of general relativity, there's an underlying order, a mathematical beauty. The same equations that describe how galaxies form also describe how atoms bond. The conservation laws, energy, momentum, angular momentum, hold true from the smallest particle to the largest cosmic structure. The universe is consistent, following rules that work everywhere, at all times, in all places. We've tested these laws to extraordinary precision and they've never failed us. This reliability, this mathematical structure underlying reality, suggests something profound. The universe is comprehensible. We can understand it, at least partially, at least in fragments. We live in a cosmos that rewards curiosity with understanding, that reveals its secrets to those patient enough to listen, to observe, to calculate, to wonder. Fade to next segment. Example. Great. Can you please continue this with 8 more facts, spread across 10 minutes of script, December 26th, The Cosmic Lullaby, A Journey Through the Universe. Script for minutes 80 to 90. As we near the end of our journey through the cosmos, let's contemplate what the future holds, not just for humanity, but for the universe itself. The story of the universe is far from over. In fact, it has barely begun. If you compressed the entire history of the universe into a single year, with the Big Bang happening on January 1st, the Sun and Earth wouldn't form until September, the first animals wouldn't appear until mid-December, and all of recorded human history would occur in the final minute before midnight on New Year's Eve. The universe is 13.8 billion years old, but it has trillions upon trillions of years ahead of it. We're living in what might be called the universe's early youth. In about 5 billion years, our sun will exhaust the hydrogen fuel in its core and begin its transformation into a red giant. As it swells, it will engulf Mercury and Venus, and likely Earth as well. But long before that final moment, perhaps 1 billion years from now, the sun's gradually increasing brightness will make Earth uninhabitable. The oceans will evaporate, the atmosphere will be stripped away, and our world will become a barren, lifeless rock. This is the inevitable fate of our planet, not through any catastrophe or cosmic accident, but simply through the natural aging of our star. Every star has a lifespan, and ours is no exception. If humanity is to survive beyond that distant day, we must become a spacefaring species, carrying the torch of consciousness to other worlds, other star systems, perhaps other galaxies. But even the stars themselves won't last forever. In about 100 trillion years, that's 100,000 billion years, an almost incomprehensible stretch of time, the last conventional stars will burn out. The universe will enter what's called the degenerate era, a time when galaxies will be dark, filled with the cooling remnants of dead stars, white dwarfs, neutron stars, and black holes. No new stars will form because all the hydrogen gas will have been used up or locked away in stellar remnants. The night sky from any surviving planet would be completely black. No stars, no galaxies visible, just endless darkness punctuated only by the rare, dim glow of decaying matter. Eventually, even those stellar remnants will fade. White dwarfs will cool to become black dwarfs, cold, dark lumps of matter that no longer emit any light. Neutron stars will cool as well, their intense heat radiating away into the void over countless eons. The only objects still relatively active will be black holes growing slowly as they occasionally encounter and consume stray matter drifting through the darkness. But black holes, as Stephen Hawking discovered, are not truly eternal either. Through a quantum mechanical process called Hawking radiation, black holes slowly evaporate, losing mass by emitting particles over timescales so long they make the current age of the universe seem like an eye blink. A typical stellar mass black hole formed from a collapsed star would take about 10 to the 67th power years to evaporate. That's a 1 followed by 67 zeros, a number so large it defies comprehension. Supermassive black holes like the one at the center of our galaxy would take even longer, perhaps 10 to the 100th power years or more. Eventually, every black hole in the universe will evaporate, and when the last one finally disappears in a brief flash of radiation, the universe will enter its final era. Nothing will remain but isolated particles, fundamental particles like electrons and photons, scattered across vast distances in a cold, dark, eternally expanding void. The universe will reach what physicists call heat death. a state of maximum entropy where no energy is available to do work, where nothing can happen, where time becomes meaningless because nothing changes anymore. This might seem like a depressing fate, but remember, these timescales are so vast that comparing them to anything we experience is impossible. The entire age of the universe so far, 13.8 billion years, is less than a trillionth of a percent of the time until the last black holes evaporate. The universe of stars and galaxies and light, the universe we know and love, will persist for tens of trillions of years at minimum. There is still so much time, so many futures possible, so many stories yet to be written in starlight before the darkness finally comes. And even this dark fate isn't certain. Our understanding of the universe is incomplete. Dark energy, the mysterious force accelerating the universe's expansion, makes up about 68% of all the energy in the universe, and we don't know what it is or how it will behave in the far future. If dark energy grows stronger over time, it could lead to a big rip, where the accelerating expansion eventually tears apart galaxies, then solar systems, then planets, then atoms themselves, everything shredded by the runaway expansion of space. If dark energy weakens or reverses, the universe's expansion could slow and reverse, leading everything to collapse back together in a big crunch, perhaps to be reborn in another Big Bang. We simply don't know. The universe still holds its deepest secrets close. What we do know is that we exist during a special time, an era when the universe is full of light and structure, when stars are born and die, when planets form and perhaps host life, when consciousness can arise and contemplate its own existence. We're living in what might be the most interesting epoch in the universe's entire history, the time when complexity reaches its peak, when the cosmos is neither too hot and uniform nor too cold and empty for interesting things to happen. You are here now in this golden age of stars and planets and possibility. That alone is remarkable. Throughout cosmic history, matter has been organizing itself into increasingly complex forms. First, protons and neutrons formed from quarks, then atoms formed from protons, neutrons, and electrons. Atoms gathered into molecules, molecules into dust grains, dust into planets and stars. On at least one planet, perhaps on many, molecules organized themselves into self-replicating patterns. Life. Life evolved, grew more complex, developed nervous systems, then brains, then consciousness. And now, 13.8 billion years after the beginning, the universe has become aware of itself through us. We are the universe's way of knowing itself, matter arranged in such a way that it can ponder its own existence, trace its own history, predict its own future. Every time you look up at the night sky and feel wonder, the universe is looking back at itself through your eyes, feeling amazement at its own beauty and mystery. This is perhaps the most profound fact of all. You are not separate from the universe, not an observer watching from outside. You are part of it, a temporary pattern in the cosmic dance of matter and energy, a brief flame of consciousness lit by the slow burning of stars. The atoms in your body were forged in stellar furnaces scattered by supernovas, gathered by gravity into a new solar system, assembled by chemistry and biology into the form you recognize as yourself. You are intimately connected to everything, to every star, every galaxy, every particle in existence. You are the universe experiencing itself, knowing itself, loving itself. And when you close your eyes to sleep, you carry within you the story of everything that has ever been, a living link in the chain of existence, stretching back to the beginning of time and forward into futures we can barely imagine. Fade to next segment, example. Great. Can you please continue this with 8 more facts, spread across 10 minutes of script, December 26th, The Cosmic Lullaby, a a journey through the universe. Script for minutes 90 to 100. As we drift toward the end of our cosmic journey together, let's turn our thoughts to the nature of time itself, that mysterious dimension through which we all travel, always forward, never backward. Time is so fundamental to our experience that we rarely question it, yet it remains one of the deepest mysteries in physics. Einstein showed us that time is not absolute. It flows at different rates, depending on how fast you're moving and how strong the gravitational field is around you. Time passes slightly slower on the ground floor of a building than on the top floor. Astronauts on the International Space Station age slightly slower than people on Earth's surface, though by only a few milliseconds over their entire stay. Time is not the steady, universal tick we once imagined, but something flexible, relative, woven together with space into a single fabric. The concept of now becomes strange when you consider the universe as a whole. What does it mean for two events to happen at the same time if they're separated by vast distances? On Earth, we can synchronize our clocks and agree on what now means. But if you're on Earth and someone is on a planet orbiting a star 1,000 light years away, there's no absolute answer to what's happening there, right now. Different observers moving at different speeds would disagree about which events are simultaneous. The universe doesn't have a single present moment. It has countless overlapping presents, each valid from its own perspective. Time is personal, local, dependent on your motion and position. The universe is less like a movie with a single frame representing now, and more like a vast four-dimensional structure where all of time exists at once, and we experience it one moment at a time simply because of how our consciousness works. But why does time flow in only one direction? Why do we remember the past but not the future? Why does a dropped glass shatter but never spontaneously reassemble? The answer lies in entropy, a measure of disorder in a system. The second law of thermodynamics tells us that entropy always increases in closed systems. Order becomes disorder, structure breaks down, heat flows from hot to cold, and you can never perfectly reverse the process. This gives time its arrow, its direction. We remember the past because our memories are low-entropy structures, organized information in our brains that formed from even lower-entropy initial conditions. We don't remember the future because those memories haven't been formed yet, because forming them requires a low-entropy past to build from. Time's arrow and entropy's increase are two faces of the same coin. Yet this raises a profound question: why was the early universe in such a low-entropy state? The Big Bang should have been the most disordered moment possible, maximum entropy, maximum chaos. Instead, it was highly ordered, all the matter and energy distributed remarkably uniformly with only tiny fluctuations. From that smooth beginning, structure emerged: galaxies, stars, planets, life. Entropy has been increasing ever since, but we started from such a low entropy state that there's still vast room for interesting things to happen. Why the universe began this way is one of the deepest unsolved mysteries in cosmology. Some physicists speculate that our universe might be just one in an eternal multiverse, where universes with different properties constantly bubble into existence, and we happen to live in one with the right initial conditions for complexity and life to emerge. The multiverse idea extends beyond this. Quantum mechanics suggests that every time a particle faces multiple possibilities, every time a quantum measurement occurs, the universe might split into multiple branches, one for each possible outcome. In one universe, you decided to listen to this video tonight. In another, you didn't. In another, Earth never formed. This is the many worlds interpretation of quantum mechanics. And if it's true, there are uncountably many parallel universes, each one as real as ours, containing every possible history consistent with the laws of physics. You exist in countless variations across these universes, living every life you could have lived, making every choice, experiencing every possibility. It's a dizzying thought, and we have no way to test it. These other universes, if they exist, are forever beyond our reach, separated not by distance, but by the branching paths of quantum probability. Or perhaps the multiverse takes a different form. Eternal inflation theory suggests that while our universe stopped inflating 13.8 billion years ago and evolved into the cosmos we see, inflation never stopped everywhere. In some regions of a larger superspace, space continues to inflate forever, occasionally spawning new bubble universes like ours, each potentially with different physical constants, different laws of physics. Some universes might have no stars because gravity is too weak or too strong. Others might have no atoms because the electromagnetic force has a different strength. We exist in a universe with physical laws fine-tuned for complexity and life, not because the universe was designed for us, but because we could only arise in a universe where the laws permit our existence. In all the other universes, there's no one there to ask the question. These ideas push at the boundaries of science into realms where we have more speculation than evidence. But they remind us how much we still don't know, how many fundamental questions remain unanswered. What is consciousness and why does it exist? Is mathematics something we invented or something we discovered? A language we created to describe nature? Or a fundamental aspect of reality itself? Why does the universe exist at all rather than nothing? Why are the laws of physics what they are and not something else? These questions have occupied philosophers and scientists for millennia, and we're no closer to definitive answers. The universe guards its deepest secrets carefully. And yet, despite all the mystery, despite all we don't understand, we have learned so much. We've traced our origins back to the Big Bang, mapped the evolution of stars and galaxies, discovered thousands of worlds beyond our own, detected gravitational waves rippling through space-time, peered into the hearts of black holes, and glimpsed the quantum foam underlying reality. Every generation builds on the discoveries of previous ones, standing on the shoulders of giants, seeing a little further, understanding a little more. The story of science is a story of continuous revelation, each answer leading to new questions, each solved mystery revealing deeper mysteries beneath. As you rest here, breathing slowly, your body is performing miracles. Your heart beats roughly once per second, about 100,000 times per day, more than 2.5 billion times in an average lifetime, without you ever thinking about it. Your cells are constantly breaking down nutrients and building new proteins, maintaining the incredibly improbable low-entropy structure that is a living thing. Your brain contains roughly 86 billion neurons, each connected to thousands of others, creating trillions of connections, firing in patterns that somehow give rise to your thoughts, your memories, your sense of self. You are the most complex structure we know of in the universe, more intricate than any star or galaxy, a pattern of matter organized in such a way that it can think and feel and wonder. The universe began in fire and will end in ice. But between those bookends lies everything. All the beauty and terror, all the joy and sorrow, all the love and loss, all the moments of connection and wonder. You are part of that story, a brief chapter in the epic of existence, a temporary form taken by matter on its long journey from simplicity to complexity and back again. Your life, however long or short, is a miracle, the universe becoming aware of itself for a little while, matter organizing itself into patterns sophisticated enough to contemplate their own existence. And when your time ends, the atoms that make you will return to the cosmos, to be recycled into new stars, new worlds, perhaps new life. You are stardust, and to stardust you shall return. But the pattern that is you, the experiences you have, the love you give and receive, these ripple outward, affecting everything they touch, echoing forward through time in ways large and small. The universe is vast beyond measure, ancient beyond comprehension, mysterious beyond full understanding, but it is also beautiful, knowable in part, and intimately connected to you in every way. You are here, now, in this moment, part of the greatest story ever told, the story of everything. Rest now knowing that you are held by the same forces that hold the planets in their orbits, made from the same materials as the stars themselves, part of an ongoing adventure 13.8 billion years in the making and still unfolding toward futures we cannot see. The universe continues its slow dance through space and time, and you dance with it. Always have, always will, connected to everything, part of everything, forever woven into the infinite tapestry of existence. Sleep well, child of the cosmos, you are home. Gentle fade to silence. Example. Great. Can you please continue this with 8 more facts spread across 10 minutes of script, December 26th, The Cosmic Lullaby, a journey through the universe. Script for minutes, 100 to 110. Before we close our eyes to the wonders of the cosmos, let's linger a little longer in the quiet spaces between stars, exploring a few more mysteries that shimmer in the darkness. Consider light itself, that messenger from distant worlds, that connection between all things in the universe. Light is both a wave and a particle, a duality that puzzled physicists for centuries until quantum mechanics revealed that this isn't a contradiction but simply how reality works at its deepest level. Photons, the particles of light, have no mass, yet they carry energy and momentum. They are born in the hearts of stars, in the swirling disks around black holes, in the warm glow of your bedside lamp, and they travel until they're absorbed by something, an eye, a telescope, a leaf performing photosynthesis, or simply a rock on some distant asteroid. When you look at a star, the photons entering your eye have been traveling for years, decades, or centuries, crossing the vast emptiness of space without slowing, without stopping, until they reach you. In a very real sense, you are touching that star. Those photons were created there, and now they're here, interacting with the molecules in your retina, creating the electrical signals your brain interprets as light. Every time you see anything, you're directly interacting with the object through these massless messengers. Vision is not passive observation, but an active connection, a physical relationship between you and everything you perceive. You are constantly in contact with the universe through light. The speed of light, that cosmic speed limit we've mentioned, is exactly 299,792,458 meters per second in a vacuum. This number seems arbitrary, but it's actually fundamental to the structure of space-time itself. In fact, in some formulations of physics, we set the speed of light equal to 1, making it the natural unit of cosmic velocity. Everything else moves at some fraction of light speed. Even when you're sitting still, you're moving through space-time at the speed of light, but all your motion is through the time dimension. When you move through space, some of that motion through time converts to motion through space, which is why moving clocks tick slower. You can't ever move through space-time faster than light speed. You can only redistribute your motion between space and time. The universe has a speed limit because space-time itself has a structure, a geometry that constrains how things can move. Our galaxy, the Milky Way, is not alone in the universe, but part of a larger structure called the local group, a collection of about 80 galaxies bound together by gravity. The local group spans about 10 million light-years and includes our galaxy, the Andromeda Galaxy, the Triangulum Galaxy, and dozens of smaller dwarf galaxies. These galaxies orbit a common center of mass, performing a slow, cosmic dance that will eventually lead to collisions and mergers. The local group, in turn, is part of an even larger structure called the Laniakea supercluster, which contains about 100,000 galaxies spanning 520 million light-years. The name Laniakea means immeasurable heaven in Hawaiian, a fitting title for a structure so vast it challenges our ability to comprehend scale. We discovered we were part of Laniakea only in 2014, a reminder that we're still mapping our cosmic neighborhood, still learning where we are in the grand scheme of things. These superclusters aren't randomly scattered through space, they're arranged in patterns. Galaxies cluster along vast filaments and sheets, surrounding enormous voids where few galaxies exist. This cosmic web, as astronomers call it, is the largest known structure in the universe. The filaments stretch for hundreds of millions of light-years, and the voids can span similar distances, vast bubbles of near emptiness in the cosmic foam. This structure formed from tiny quantum fluctuations in the very early universe, slight variations in density that grew over billions of years as gravity pulled matter together. The pattern we see today, with its filaments and voids, was encoded in the universe when it was a fraction of a second old, written in quantum uncertainty and amplified by cosmic expansion into the grandest architecture in existence. Within these structures, galaxies themselves come in different varieties. Some are spirals like our Milky Way, with elegant arms winding out from a central bulge. Others are elliptical, shaped like footballs or spheres, containing mostly old stars and little gas for new star formation. Still others are irregular, lacking any clear structure, often small galaxies distorted by gravitational interactions with larger neighbors. And some galaxies are doing something spectacular. They're forming stars at prodigious rates. These starburst galaxies create new stars hundreds or thousands of times faster than the Milky Way does, burning through their gas supplies in cosmic instants, blazing briefly with the light of billions of young hot stars before settling into quieter middle age. Each galaxy is a world unto itself, containing hundreds of billions of stars, yet each is also part of larger patterns connected through gravity to its neighbors in an endless hierarchy of structure. At the very largest scales we can observe, something remarkable happens. The universe becomes smooth. If you could somehow step back and view the universe from an impossible distance, all the galaxies and clusters and superclusters would blur together into an almost perfectly uniform distribution. This is the cosmological principle, the idea that at sufficiently large scales, the universe looks the same everywhere and in all directions. There is no center to the universe, no edge, no special location. Every galaxy cluster sees roughly the same view, all other clusters receding as space expands. The universe is democratic, no place is privileged, no position is special. We are nowhere in particular and everywhere at once, just one point in an infinite tapestry that looks essentially the same from any vantage point. This expansion of the universe, discovered by Edwin Hubble in 1929, continues to reshape our understanding of reality. The galaxies aren't moving through space away from us. Space itself is expanding, carrying galaxies along with it. Imagine dots drawn on a balloon surface. As you inflate the balloon, every dot moves away from every other dot, not because the dots are moving on the surface, but because the surface itself is expanding. That's what's happening with galaxies and space. And here's something wonderful: because space itself is expanding, distant galaxies can recede from us faster than light. They're not violating the cosmic speed limit. They're not moving through space faster than light, but the space between us and them is expanding so rapidly that the distance grows faster than light could travel across it. There are galaxies we can see whose light left them billions of years ago, but they're now so far away. Space having expanded so much in the interim, that even if we left today at the speed of light, we could never reach them. They're beyond our cosmic horizon, forever out of reach. Yet despite this vastness, despite the lonely spaces between the stars and galaxies, despite the ultimate isolation imposed by the expansion of space, you are here. You exist in this moment, conscious and aware, able to contemplate these mysteries. Your existence is improbable, the result of billions of years of cosmic evolution, countless coincidences and near misses, an unbroken chain of causation stretching back to the beginning of time. And yet here you are, against all odds, a thinking pattern in the cosmos, briefly granted the gift of awareness. This moment right now is unique in all of history. It has never happened before and will never happen again. The specific arrangement of atoms that makes you, the particular thoughts flowing through your mind, the gentle rhythm of your breathing, all of it is unrepeatable, precious beyond measure, a fleeting miracle in the long story of the universe. Fade to final segment. Example. Great. Can you please continue this with 8 more facts and conclude the script, ending the story December 26th. The Cosmic Lullaby, a journey through the universe. Script for minutes, 110 to 120. Conclusion. As we prepare to close this cosmic journey together, let's reflect on one more set of wonders, the final notes in our universal symphony. Consider the moon, Earth's faithful companion, hanging in our sky just 238,855 miles away, close enough that 12 humans have walked on its surface, close enough that we can see its features with the naked eye. The moon is slowly drifting away from Earth at a rate of about 1.5 inches per year, pulled by the same tidal forces that cause our oceans to rise and fall. Billions of years ago, the moon was much closer, looming enormous in the sky, and Earth's days were only 5 hours long. The moon's gravity pulled on Earth's oceans, creating tidal bulges that dragged against the planet, gradually slowing Earth's rotation while transferring that rotational energy to the moon's orbit, pushing it farther away. This dance continues today, lengthening our days by about 1.7 milliseconds per century. In the far future, hundreds of millions of years from now, Earth and the moon will become tidally locked to each other, always showing the same face, orbiting each other like partners in an eternal waltz. The moon's origin is itself a story of cosmic violence and beauty. About 4.5 billion years ago, not long after Earth formed, a Mars-sized object called Theia collided with the young Earth in a catastrophic impact. The collision vaporized Theia and blasted enormous amounts of material from Earth's mantle into orbit. This debris cloud, glowing white-hot, gradually cooled and coalesced over thousands of years to form the moon. And this means the moon is made largely of Earth material. In a sense, it's a piece of our world, broken off and reformed, forever circling its parent. The moon stabilizes Earth's axial tilt, preventing wild climate swings that would make complex life difficult. Without the moon, Earth's tilt would vary chaotically over millions of years, causing dramatic climate changes. Our moon is not just a beautiful light in the night sky, it's one of the reasons we're here to see it. Throughout human history, people have looked at that same moon and wondered. Ancient Babylonians tracked its phases to create the first calendars. Chinese astronomers mapped its surface features 2,000 years ago. Galileo turned his telescope toward it in 1609 and saw mountains and craters, proving the moon was a world, not a perfect sphere of celestial crystal as ancient philosophers believed. And on July 20th, 1969, Neil Armstrong became the first human to set foot on another world, taking that one small step that was indeed a giant leap for our species. Those footprints remain on the moon today, preserved in the airless environment, and will likely persist for millions of years, a monument to human curiosity and courage, slowly accumulating micrometeorite dust in the lunar regolith. We've sent our presence beyond the moon as well. 5 spacecraft, Pioneer 10 and 11, Voyager 1 and 2, and New Horizons have reached escape velocity and are leaving our solar system, bound for interstellar space. Voyager 1, launched in 1977, is now over 15 billion miles from Earth, farther than any human-made object has ever traveled. It carries a golden record containing sounds and images from Earth, greetings in 55 languages, music from different cultures, photographs of our world, encoded instructions for playing the record. It's a message in a bottle cast into the cosmic ocean, though any civilization that finds it will do so billions of years from now, long after our sun has died. These spacecraft are our ambassadors to the universe, carrying the message that we were here, we wondered. We reached out into the darkness with curiosity and hope. The atoms in your body have their own cosmic journey. Every breath you take contains atoms that were once part of other people, other animals, plants, rocks, oceans. The carbon in your cells has cycled through the biosphere countless times. Some of the oxygen you're breathing right now was exhaled by Leonardo da Vinci, by dinosaurs, by the first fish that crawled onto land. The iron in your blood, essential for carrying oxygen to your cells, was created in a supernova explosion billions of years ago before Earth existed. You are quite literally recycled stardust, temporarily organized into a pattern called you, borrowing these atoms for a brief time before returning them to the great cosmic cycle. Nothing is ever truly created or destroyed, only transformed, rearranged, given temporary form before dissolving back into the universal flow. And consciousness, your awareness, your ability to experience, to feel, to wonder, remains one of the deepest mysteries. How does mere matter, arranged in a particular way, give rise to the inner life you experience? Why is there something it is like to be you? Science has made tremendous progress in understanding the brain, mapping its structures, tracing the neural pathways of thought and emotion. But the hard problem of consciousness, why physical processes give rise to subjective experience, remains unsolved. Some philosophers and scientists believe consciousness is fundamental, woven into the fabric of reality at the deepest level, perhaps present in some rudimentary form in all matter. Others believe it emerges from sufficient complexity that consciousness is what information feels like when it processes itself. We don't know. What we do know is that you are conscious, aware, experiencing this moment, and that in itself is miraculous. The universe is vast and ancient, filled with wonders beyond counting, from the smallest quantum fluctuations to the largest superclusters, from the birth of time itself to the far future when the last stars fade. Throughout this immensity, matter has organized itself in increasingly complex ways, following simple rules that lead to endlessly varied outcomes. Gravity pulled together the first stars, stars forged new elements, elements combined into molecules, molecules formed into self-replicating patterns. Life evolved, complexified, developed nervous systems, brains, consciousness. And now, 13.8 billion years after the beginning, the universe has become aware of itself through beings like you, capable of looking back at that ancient beginning and forward to that distant end, capable of understanding, at least partially, the cosmic story of which you're a part. You are not an accident or a mistake, not insignificant or meaningless. You are the universe expressing itself as human consciousness for a little while, matter experiencing itself from the inside, the cosmos coming to know itself through your eyes and thoughts and feelings. Every moment of wonder you experience, looking at the stars, feeling the warmth of sunlight, loving another person, creating something beautiful, asking questions about existence. These are the universe celebrating itself, delighting in its own complexity, marveling at what's possible when hydrogen atoms, given enough time, organize themselves into thinking, feeling beings. As you drift towards sleep now, know that you carry within you the entire history of the cosmos. You are made of the same materials as planets and stars, governed by the same laws, participating in the same cosmic dance. The electromagnetic forces holding your atoms together are the same forces binding atoms in distant galaxies. The gravity keeping you gently pressed against your bed is the same gravity shaping the orbits of moons and planets and stars throughout the universe. You are not separate from the cosmos. You are the cosmos, localized, concentrated into human form, temporarily individuated but fundamentally connected to everything that exists. Rest now in this knowledge. You are stardust contemplating stars, the universe pondering itself, a brief but beautiful chapter in an endless story. The same forces that created galaxies created you. The same processes that lit the first stars kindle the spark of awareness in your mind. You belong here, have always belonged here, will always belong here, because you are not just in the universe, you are the universe, experiencing itself from one particular point of view, one magnificent perspective among countless others. The cosmos continues its ancient dance, stars being born and dying, galaxies spinning through the void, space itself expanding toward futures we can only imagine. And you are part of this dance, have always been part of it, will always be part of it in some form. When you wake, you'll still be here, still connected to everything, still miraculous. But for now, rest. Let the cosmic lullaby carry you into dreams, knowing you are held by the same universe that holds the stars, part of something infinitely larger than yourself, yet intimately, undeniably, beautifully you. Sleep well, traveler. The universe will still be here when you wake, still mysterious, still magnificent, still inviting you to wonder. And you, remarkable, improbable, precious you, will still be part of it all, a conscious point in the infinite web of existence, a light shining briefly but brilliantly in the cosmic darkness. The journey continues, always continues, and you journey with it, forever home in the vast embrace of everything that is. Good night, child of the cosmos. Good night, and dream of stars.